All right, so we're going to finish our chapter 6. We're going to start by talking about electronegativity and bond polarity. So we mentioned electronegativity a little bit last time with putting the least electronegative element in the middle of your Lewis structure, but we're going to talk about what that is. So what is electronegativity? Electronegativity is how much an atom pulls another atom, pulls the other atom's electrons when in a bond. Okay, so when I'm in a bonding situation, how much an atom pulls another atom's electrons. So if I'm very electronegative, like fluorine is very electronegative, has a very high number here, that means I'm going to pull other atoms' electrons a lot. And that makes sense for fluorine, right? Because fluorine really, really wants another electron. Versus if you look down here, they don't even have francium on this list, but it would be down here below cesium, right? It's very, very, very low. So low electronegativity. Electronegativity decreasing as I go down and increasing as I go across. Francium does not even want its own electrons, let alone pull another atom's electrons. So if I put an atom that really, really wants electrons with an atom that really, really, really doesn't want electrons, then I'm going to have a big electronegativity difference. So a large electronegativity difference in a bond means that bond is going to be really uneven. It's going to be really unequal with how it shares electrons. So if we're looking here at what that means, it means polarity. So if you have something that is nonpolar, okay, so does not have poles, it is not polarizing, and no poles, so no like north and south, positive and negative areas. If you have an equal sharing of electrons, you're going to be nonpolar. So if I have two hydrogens sharing together, they're going to share equally, right? Because you share best with yourself. So if hydrogen's hanging out with another hydrogen, they're going to be sharing very equally. That means that most of the time the electrons are going to be shared in the middle of these hydrogens. Both hydrogens have access to the electron. No one hydrogen is pulling more than the other. But if we look at the other example, we have an unequal sharing of electrons. This is called a polar covalent bond. Notice that these are both covalent, so they're both sharing. It's just the one is sharing really well, the hydrogen is sharing really good, and then this hydrogen chloride or hydrochloric acid, depending on what you look at. So, for example, this would be hydrogen chloride, but with the AQ at the end, like we talked about, that would be the acid version. But it doesn't matter. Either one is very polar. So hydrogen has a very low electronegativity, well, a relatively low electronegativity of 2.1. Chlorine is 3.0, so it has a difference of 0.9. So that makes a polar bond. The chlorine is pulling the electrons more than the hydrogen is. So the chlorine is kind of hogging the electrons. So how we write that is with this little, increase to show you, this little delta. It's a Greek baby delta. It's like, it means partial. So that's a partial negative. It's not really a full negative like ion, but that's a partial negative and that's a partial positive here. And that just means that, hey, this side of the molecule is a little more positive and this side's a little more negative. This side is more negative because the chlorine is hogging all the electrons. It's pulling all the electrons more towards it. And so that's why that would be considered more negative. And so looking a little closer at nonpolar covalent bonds, you can actually tell by looking at the numbers given in an electronegativity table like this. You will always be given a table. I'll never expect you to know these numbers. But if you do notice that the further apart two elements are on the table, the more their electronegativity difference. So if you have elements that are far apart, they're going to be more polar if you put them together. So for nonpolar, we have some atoms putting together like this. What I want you to remember if they're the same element, non-polar. Or if it's carbon, hydrogen, non-polar. Otherwise, you have to be given a table to tell. So instead of having you memorize like all these different examples, I'm just going to have you say if is it the same element, it's nonpolar. If it's CH, it's nonpolar. But that's it. So like if it's NN, it's nonpolar. If it is HH, it's nonpolar. If it's OO, it's nonpolar. Okay, that's what I want you to know. But if you do have numbers, you can tell it's a very small difference. I would say less than 0.5 would be nonpolar. Or yeah, less than 0.5. So if you look at polar covalent 5s, they're going to be polar covalent bonds 0.5 or higher if it's still covalent. So I've got two nonmetals, but they're a little bit more of a difference in their electronegativity. So what I want you to remember not the same element, not CH, polar. So if it's not the same element and it's not CH, then it's polar. So I would check to see, is it nonpolar first? Is it the same element or is it CH? If it's neither of those things, then call it a polar bond and be done with it. And then you have, if it's more polar than this, it'll be ionic. So it'll be a metal and a nonmetal. So ionic is like super duper polar. So a dipole is kind of the noun for what we use for this kind of showing this bond. So this is a dipole. It's just a representation of a positive side and then the direction of electrons, the electron pull. So we always do the arrow towards the more electronegative element. So this is more electronegative. This is less electronegative. How am I looking at that? I'm just looking on the periodic table. So I'm going to see if I have a polar bond, right, you're going to remember two different elements. The more electronegative one is going to be whatever one is closest to my buddy fluorine, because it's the most electronegative. So if I'm looking at these bonds here, carbon or oxygen, well, oxygen's closer to fluorine, so it's more electronegative. Oxygen is right next to fluorine, so it's more electronegative. So that's why it's going to be negative here. And then you have actual fluorine here, so it's going to be the one that's most negative. So we draw this direction of electron flow towards the more electronegative. And then we give ourselves this little plus that goes with this plus. So these are called partial charges, and these are called dipoles. You'll be asked to write both of these or label both of these in study assignment 8. And then, like I said before, if you get over like 1.5, I think, greater than 1.5, it's considered ionic, but you don't need to look at electronegativity differences to tell ionic. We can actually just look at the type of atoms and see, oh, I have a metal and a nonmetal, so it's ionic. That's like the most polar that you can get, essentially, is that it just completely separates into charges. It's not sharing electrons anymore. So here's your chart, sorry, 0.5 and 1.8, but you don't need to know this again. I want you just to go back and remember if they're the same element or not, or if they're CH. Here's some more examples of some pictures kind of showing you purple is electron dense, or dark purple is electron dense, and pink is not a lot of electrons. And so you can see some visual representation. See how ionic is like totally separated, it's totally cut off. So we've talked a little bit at the very end of class about shapes, but polarity is really going to help us with putting shapes and polarity of molecules. We've been talking about polarity of bonds. This is bond polarity. Okay. Next, we're going to be talking about the polarity of molecules. of whole molecules. So, for example, let's just look. The CH bond, is that polar or nonpolar? Right, the CH bond is nonpolar, because it's the one exception nonpolar I'm asking you about, but the whole molecule may be polar or nonpolar, depending on what kind of shape it's in. So, we're going to look at different shapes. The shapes are a theory called VSEPR theory, valence shell electron pair repulsion. So all you really need to know about this is that electrons on the outside repel each other. So they try to be as far apart as possible, which makes sense. So let's look at some of these shapes. Linear is our first shape. You're going to see in the chart that you're going to have on your green sheet. Linear, we have two electron areas around the center atom, and so as far apart as they can be is 180. So this is a linear shape. Trigonal planar is we have three areas of electrons, so three electron areas around the center atom. So they're going to be as far apart as they can, which is 120, so they're going to be trigonal planar. So it's a flat triangle. So we can imagine that this is a triangle. Then we can also have three electron groups, but we don't call it trigonal planar. So trigonal planar, we have to have three corners of a triangle. But if we look here, so look around the sulfur, the center atom. I have 1, 2, 3 areas of electrons, but one of those areas is a lone pair. And I can't actually see electrons, so I really only see my atoms like this. And so I get this part of a trigonal planar, but I can't see this top part. It's kind of invisible. So I just get this bent shape. So it's still 120 degrees, but I just can't see the top. I don't have this top part of the triangle here to make it a triangle. So I just have this section that just kind of looks bent. So that's why I call it bent. Then you're going to have tetrahedral. Tetrahedral, tetra, think 4, is 4 electron areas around the center atom. And all of those electrons are bonds. So I get this tetrahedral shape. A tetrahedron is a 3D structure. So if you look over here at this model right here, you have this line and wedge, this wedge and dash notation. The wedge means it's coming out of the page at us, and the dash means it's going back into the page. So that's kind of how you can read that. So kind of think of it as a 3D thing, and I'll have this in class to show you too. Now, trigonal pyramidal is just like tetrahedral. I have 4 electron areas, but one of them is a lone pair. So I get this kind of weird pyramid kind of thing. So I call it trigonal pyramidal. Then if you, that's the second slide. If you remove another one of the electron groups, so I have 4 electron areas here, so it has a tetrahedral electron geometry. But again, you have to remove the electrons because we don't actually see them, so we get this bent shape. So you're going to have this on every test or quiz, so don't worry about memorizing them, but know how to use this chart. Look around the central atom for all of these. And then you have some examples here. Okay, so hydrosulfuric acid. Let's draw the Lewis structure. So pause if you want to and then catch up with me. I'm going to draw the Lewis structure like this. Hydrosulfuric acid is H2S aqueous. Okay. I've got 1, 2, 3, 4 electron groups, so I'm going to kind of maybe draw it in what I would think would be like a tetrahedral kind of shape. Okay, and I have some dots hanging out over here. But if I can't see the electron pairs, right, I'm going to have this bent shape. So I can look at this chart and I can see, okay, I've got 4 things around the center atom, and I've got 2 lone pairs, so it's bent. This is the 2 lone pairs around the center atom here. Alright, so quickly only have, actually I have to do this in 2 videos. So this is video 1, and we'll come back to polarity in video 2.